Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know about surds for your upcoming test. So a C-level student would know that a to the power of b over c equals the cth root of a to the power of b. A C-level student would be able to convert between fractional indices and surds. So for example, they would know that x to the power of 3 over 4, the bottom number tells you which root it is, and the top number gives you the power. They'd be able to take something like fifth root of, say, x squared and convert that into a fractional index. Power on top, which root it is on the bottom. That's easy. So surds come from fractional indices. We also need to be able to perform operations with them. So a C-level student would be able to perform an operation like this. They would know that you can only add and subtract like surds with the same number under the square root. So in order to simplify this, we would treat these like surds. So 2 root 3 minus root 3 is just root 3. Negative 3 root 5 plus 2 root 5, well, negative 3 plus 2 is negative 1, so you just get negative root 5. That's our final answer. Now just note, this is said to be in exact form because this is exactly the answer. If we were to round this, put it in our calculator, that would not be exact. So that's basically C level. What about a student who's at a B level? So here's an example of a B-level question. See, this is like the question we had on the previous slide where you were just subtracting surds, but there's a trick to it. That's basically what B-level questions are. C-level questions, but with a trick to them. See, the trick here is that the numbers under the square root are not equal. It looks like we can't actually perform this operation. The trick is we need to first simplify each of these surds. Okay, so how do you simplify surds? Well, you need to find the highest square number, highest perfect square that is a factor of each of these. So for 600, I'm hoping you can see that 600 can be written as 6 times 100. So you might be thinking, okay, why don't you use 6 times 100? There are plenty of other pairs of factors of 600. I could have chosen 4 times 150, 8 times 75, etc. Well, I chose these numbers because this is the highest perfect square that goes into 600. This allows me to simplify because I can write it as root 6 times root 100. Now, square root of 100, you should know, is just 10. So this can be simplified as 10 root 6. This is said to be simpler than that because there's a lower number under the square root. Okay, let's have a look at this one here. Well, we'll just leave the 3 alone for now. Now, I'm hoping that if you got a question like this, you would say to yourself, okay, well, here we have a root 6. So here, the only way we're going to be able to subtract is if we also have a root 6. So how many times 6 go into 294? It turns out it's actually 49. So 49 is a square number. So we can write this as 3 times root 6 times square root of 49. Now, 3 times root 49, 3 times 7 is 21. So this just becomes minus 21 root 6. So now we can easily simplify this. 10 root 6 minus 21 root 6. Well, 10 subtract 21 is just negative 11. This is our final answer and we're done. All right, let's look at another B-level question. So here we have a B-level question in which we'll find the hypotenuse of the right-angled triangle, which I will call C. This is a B-level question because it just involves more complex operations. In order to do this, we can't just do the normal adding, multiplying, dividing, subtracting surds. We also have a trick to this question, and that is we have to use Pythagoras. So Pythagoras' theorem tells us longer side squared equals shorter side squared plus shorter side squared. So when I talked about more complex operations, here we're going to have to square an expression like this. That actually requires FOIL. Okay, so hopefully you know by now the quick way to perform perfect binomial squares. For this one, you square the first, so 4 squared 16. You square the second. Root 7 squared is just 7 because root and square, undo each other, you're just left with 7. So in the middle here goes 2 times 4 times root 7. 2 times 4 is 8. It's 8 root 7. Okay, we're going to do the same over here. We are going to square the first, square the second. Now, squares are always positive, so that's why it's a plus 7. In the middle, 2 times 4 times negative root 7 is negative 8 root 7. So we have 8 root 7 and negative 8 root 7. That's just 0. What we actually end up with is c squared equals 16 plus 7 plus 16 plus 7. C squared equals 46. So c is just going to be the square root of 46. So can we simplify this any further? Turns out we can't. The only perfect square that goes into 46 is 1, and that doesn't really help us. So that's our final answer. C must be the square root of 46. Here we solved a more complex problem that had a trick to it. So if we can do this, we're at a B level. All right, let's look at some harder questions now. So let's calculate the area of a dodecagon whose side length is 120 centimeters squared, giving the answer in exact and simplified form. Okay, I'm going to be honest. This is just an A-level question because it takes a hell of a lot of steps, as you'll see. Now, you can probably guess if this is our formula for area of a dodecagon and the area is 120, all I'm going to do is rub out A and replace it with 120. Now, this might look like an easy equation to solve, but the fact that we need an exact and simplified form actually means there's a hell of a lot of steps to it. Okay, even though it is complicated, it isn't easy, it's still just an equation. We've solved them a million times before. Let's undo what's been done to S. So what's been done here, S was squared, then times by this to get 120. We did this last, let's undo it first. I'm going to divide each side by 3. So dividing each side by 3, I get 40 equals 2 plus root 3 in brackets S squared. Now 2 plus root 3 is just a number. It's about 3.732. So it's not a nice number to work with, but it's a number nonetheless. So the way we undo timesing by a number is to divide by a number. So I'm going to divide 40 by this number now. The problem is here, 40 over 2 root 3 is correct, but it's definitely not simplified. In order to be simplified, we're going to have to rationalize the denominator. So what do I mean by that? Well, this denominator is irrational. This is an irrational number. So what I need to do is times top and bottom by something, so I don't change the value of this fraction, but I make the denominator rational. So when you have an expression like this on the bottom, you need to times top and bottom by its conjugate. What the hell is the conjugate? It is the same expression, so it's got a 2 and a root 3. But instead of a plus between them, it's a minus. So basically, same expression with a different sign. And you might be thinking, well, how does that help? You see, when I expand this, when I do this times this, I can use the difference of two squares. Hopefully you know difference of two squares if you have a minus b and a plus b, so you've got the same thing in each brackets, but a different sign. You just square the first and square the second. So using that logic here, 2 minus root 3 times 2 plus root 3, I'm just going to end up with 2 squared is 4, root 3 squared is 3, and stick a minus between them. So what do I get on top? Well, I have to times 40 by the whole shebang. I have to go 40 times 2 is 80, 40 times negative root 3 is that. Now, lucky, it works out really well for us here because 4 minus 3 is just 1. So our answer here is just s squared equals 80 minus 40 root 3. So we wanted s, not s squared, so I'm going to square root both sides. So you might be relieved at this point to know you can just leave your answer like this. Okay, so that was our answer. In order to get to this answer, we had to show a lot of knowledge of surds, which is why this is an A-level question. Let's do one more A-level question. So another A-level question you might get, you might have to show that one expression equals another expression. On the face of it, it doesn't look like these two would be equal, but with some algebraic manipulation, we will show that they are. So this is an A-level question again because of the showing something is pretty tough, but also because we're going to have to show a really good understanding of surds. We're going to have to show in one question that we know all of the different operations. All right, so let's get to it. I'm going to start with this side and simplify it. So in order to get from here to here where there is no fraction, I got to get rid of the fraction here. So I'm going to need to combine this denominator into a single fraction. So I'm going to rewrite this 1 as root 2 on root 2. Why did I choose root 2? Well, now you can see on the bottom that here we have now two fractions with the same denominator. So we can simply convert these into one fraction. Add the numerators, root 2 plus 1, keep the same denominator. So we have 1 divided by this. So when we are dividing by a fraction, what you do is keep the first thing the same, you flip the second fraction and make it 8 times. So lucky for us, because there was a 1 there, I just have root 2 on root 2 plus 1. I don't really need to write that. Okay, so how does this equal that? Well, we're going to, again, rationalize the denominator. We're going to times top and bottom by the conjugate. So the conjugate has root 2 and 1, but instead of having a plus, it is a minus. So that means that on the bottom, we're going to get, so using difference of two squares, you just square the first, square the second, stick a minus between them. On the top, root 2 times root 2 is 2. Root 2 times negative 1 is minus root 2. Once again, this is 1 on the bottom, so I don't even need to write it. I can just get rid of it. So we've shown from starting here and going all through here that 1 over 1 plus 1 on root 2 is indeed 2 minus root 2. We had to show a lot of different mathematical skills in this question. That's why it's A-level. All right, thank you so much for tuning into this video. Best of luck for the test, but you'll ace it. You're a superstar. This has been the luckiest maths teacher in the world. Have a great day.